The plant sat on the bank of the Fox River in Oshkosh, Wisconsin, in the winter of 1938. From the outside, it looked like any other Midwestern machine shop. Brick walls blackened by decades of foundry smoke, loading docks worn smooth by freight, the smell of cutting oil hanging in cold air that came off the water. Inside, an engineering team at Fairbanks-Morse was working through a problem that most of the American defense establishment had already decided was unsolvable. They were trying to build an opposed-piston diesel engine light enough, powerful enough, and reliable enough to propel a fleet submarine across the Pacific and back without mechanical failure in combat conditions. The Navy had been through this problem before and walked away from it. The diesel manufacturers who had tried it before them had handed back their contracts and offered apologies. What the Oshkosh plant eventually produced, through a decade of redesign, wartime production pressure, and a manufacturing decision so counterintuitive it looked like madness at the time, would go to sea aboard every fleet submarine the United States sent against Japan. The crews who ran those boats never saw the men who built the engine. They never knew the name of the engineer who solved the lubrication problem that had killed two competing designs, or the name of the plant manager who held production tolerances during the frantic expansion of 1941 and 42, when the war was already running and the boats were already needed. What they knew was that the engine started, that it ran, and that when the escort destroyers came and the boat went deep and the depth charges walked across the hull, the engine was still there waiting for them on the other side. The men in the engine room tended it in conditions that industrial health regulations would not have tolerated on shore, and the engine gave back what the design had promised: power, reliability, and the margin between survival and the alternative. The record of how that came to be is the record this account follows. If this story is pulling you in, take a second to hit the like button and subscribe, and drop a comment telling me where in the world you're watching from. It means a great deal to know who's listening. The American submarine service entered the Second World War with a problem it had carried for years without fully acknowledging. The Navy's fleet submarines, the boats designed in the 1920s and 30s to accompany surface task forces across the Pacific, required main propulsion diesel engines that could produce somewhere between 1,000 and 1,600 shaft horsepower per engine, for engines per boat, with enough reliability to sustain patrols that might run 60 days without access to a repair facility. The specifications were demanding in ways that the diesel technology of the era was not yet built to meet. The early standard was the Winton engine, a design adapted from locomotive propulsion and modified for submarine service. The Winton performed adequately under controlled conditions. In the Pacific, where submarines ran submerged through enormous thermal gradients, surfaced in a salt spray, and drove their engines at maximum continuous power for days at stretch, adequately was a word that got men killed. The engine's failure modes and extreme conditions were documented in submarine force maintenance records throughout the late 1930s. Cracked engine blocks under thermal stress, cylinder liner where that accelerated under sustained high load, lubrication failures at depth following the pressure changes of a crash dive, fuel injection timing that drifted as the engine temperature climbed through extended running. The patterns were consistent across multiple boats and multiple patrol cycles. The Bureau of Ships knew what the report said and what they implied about the Winton's suitability for the kind of war that American strategic planning was already sketching in the Pacific. The question was not whether a better engine was needed. The question was whether anyone could build one before the war those reports had been quietly anticipating finally arrived. Fairbanks-Morse had been in the power business since 1830. The company's record going into the 1930s was in stationary industrial engines, pumping equipment, and railroad locomotive power. The kind of heavy-duty, long-cycle work where an engine ran continuously for years and the cost of failure was measured in lost production rather than lost lives. The opposed-piston design the company's engineers were developing through the mid-1930s was not new in principle. The concept had been explored by European designers since the early years of diesel development. Two pistons working in opposition within a single cylinder, sharing a common combustion space, with no conventional cylinder head. What Fairbanks-Morse brought to it was a particular approach to the mechanical architecture of the crankshaft arrangement, the port timing geometry, and the scavenging system that pushed exhaust gases out and forced fresh charge air in with each cycle. The company had also spent years accumulating the kind of precision manufacturing capability that this type of engine demanded. The tolerances required by the opposed-piston design were tighter than anything the locomotive market had previously required, and the Oshkosh plant's investment in machine tool capability and quality control procedures through the mid-30s reflected an engineering culture that understood the difference between close enough and correct. The design produced a power-to-weight ratio that the single-piston diesels of the era could not match at equivalent displacement. It also eliminated the cylinder head entirely, which removed the component that had caused the most persistent thermal failure in submarine diesel service. The head gasket that failed under thermal cycling, the rocker arm geometry that went out of tolerance after extended high-load running, the valve timing that drifted as components wore, all of it replaced by a mechanical arrangement that distributed its thermal load differently and, in testing, more durably and more predictably. For a propulsion system that needed to run for months without major overhaul in waters where no repair facility existed, the implications were substantial. The Navy's Bureau of Engineering tested an early Fairbanks-Morse opposed-piston unit in 1934. The results were filed. The engine was promising. It was also not yet a submarine engine. The gap between a promising stationary test result and a certified naval propulsion unit was measured in thousands of hours of endurance testing, detailed failure analysis, and redesign cycles. The competing designs, from General Motors' Cleveland Diesel Division, from Owens Rentschler, from Winton itself, were further along that institutional path. The Fairbanks-Morse team had to compress years of development work into a period the calendar would not accommodate if the war arrived on schedule. The technical challenge that nearly ended the program before Pearl Harbor involved the lubrication system for the lower crankshaft. The opposed-piston design used two crankshafts, one at the top of the engine, one at the bottom, connected by vertical drive gears. The lower crankshaft sat in an environment where oil pooling, contamination, and pressure management under the rolling and pitching of a submarine at sea created failure conditions that bench testing in Oshkosh had not fully reproduced. The engine destroyed two test crankshaft assemblies in extended running trials in 1939. The failure analysis, conducted by Fairbanks-Morse Chief of Diesel Development Clarence Wilson and his team, identified the lubrication geometry as the primary cause. The oil feed passages were not delivering consistent pressure across the attitude changes a submarine in heavy weather imposed on the engine. Under normal industrial running conditions, the system worked. Under the dynamic loading of a boat rolling 15 degrees in a Pacific swell while the engine ran at full power, it failed. Wilson redesigned the oil feed passages, changed the bearing material specification, and added a pressure regulation circuit that maintained consistent oil delivery regardless of the engine's angle of inclination. The bearing material change required qualifying a new supplier, which the procurement chain resisted under the time pressure the contract imposed. The authorization to proceed carries Wilson's signature in the engineering revision record. The third crankshaft assembly ran to the end of the endurance schedule without failure. The Navy received the certified design specification in the spring of 1940. The production decision that followed was the one that, in retrospect, looks like the margin of victory. The Navy committed to the Fairbanks-Morse 10-cylinder opposed-piston engine as the primary propulsion plant for the Gato-Class fleet submarine program. The Gato-Class was the boat the Pacific War would be fought from, a design displacing just over 2,000 tons surfaced, carrying 24 torpedoes, with a surface range sufficient to reach the contested sea lanes around Japan from Pearl Harbor and still work a patrol area for weeks. Each boat needed 4 main propulsion diesels. The production contract specified a rate that the Oshkosh plant could not meet with its existing floor space and machine tool inventory. Fairbanks-Morse expanded. The company took on new workers in a labor market the defense buildup was already tightening, trained them on tolerances and procedures that the engine's manufacturing specification demanded, and began producing units at the rate the Navy's submarine construction schedule required. When the Japanese attacked Pearl Harbor in December 1941, the first Gato-class boats were already fitting out with Fairbanks-Morse engines in their engine rooms. The machinery that would carry the war to Japan was built and waiting. Wilson remained at the plant through the production expansion, working the manufacturing floor alongside the production engineers to ensure that the tolerances his design required were being held by the new workforce. This kind of engineering to manufacturing continuity was not universal practice in the wartime defense industry. The evidence suggests it made a measurable difference. The early production engines showed remarkably low defect rates given the speed at which they had been produced. Bureau of Ships inspection records from 1942 and 1943 show a pattern of minor issues caught and corrected at the factory rather than surfacing as operational problems aboard deployed submarines. Wilson knew what the Navy's inspectors were looking for because he had worked with them through the certification process. The production line reflected that knowledge in every unit that came off the floor. The men who ran those engines in combat were not engineers. They were machinists' mates and motor machinists' mates, rated petty officers who had learned their trade in Navy schools and on earlier boats, now responsible for keeping 4 large diesel engines alive during patrols that ran from Pearl Harbor or Brisbane or Fremantle to the sea lanes around Japan, Formosa, and the Philippine archipelago. The engine room of a fleet submarine at sea was a specific kind of environment. Heat ran consistently above 100 degrees Fahrenheit when the engines were at full power. Noise made normal conversation impossible without shouting. The constant physical vibration of 1,200 horsepower working 3 feet from where you stood transmitted itself through the deck plates and up through the soles of your feet at every moment the engines were running. The men who worked there developed an almost tactile knowledge of the machinery they tended. They could hear a bearing running warm before the oil temperature gauge moved. They could feel a change in the firing pattern of a cylinder through their shoes. The maintenance culture that grew up around the Fairbanks-Morse engine in the Pacific was built on this kind of intimate mechanical knowledge, and the engine rewarded it consistently and without drama. If this is the kind of history you want more of, subscribe and turn on notifications. There's far more in the record still to cover. Your support is what keeps these stories coming. The record of the engine's combat performance survives in the patrol reports that fleet submarines filed after each completed run. These reports, declassified in the decades after the war, contain maintenance logs and casualty reports alongside the tactical narratives, and what they show is a propulsion system performing at the level Wilson's pre-war testing had predicted. A report from USS Silversides, which completed 12 war patrols and became one of the most decorated submarines in the Pacific Fleet, records engine room entries that are almost routine in their confidence. Oil changes carried out on schedule, bearing inspections completed, a minor fuel injection adjustment made at sea and logged without drama. The engine had become infrastructure. It was the thing the crew relied on the way you rely on something that has never given you reason to doubt it. That reliability had a tactical dimension that went beyond mechanical convenience. The fleet submarines doctrine in the Pacific required surface transits of thousands of miles, diesel engines running to charge the batteries that powered the boat when submerged, and emergency surface sprints to escape enemy anti-submarine forces at speeds the battery-powered electric motors could not sustain. A submarine whose engines failed during a surface escape from a destroyer was a submarine that died. The Fairbanks-Morse engine's reliability under sustained high-power running, the kind of emergency full-power run that a boat pursued by a Japanese escort might need to maintain for hours, was not an incidental quality. The Bureau of Ships had specified it. Wilson had engineered it into the production design. The crews who ran those escapes and survived to file their patrol reports were the confirmation that the specification had been met. Consider what the engine's performance record meant in specific terms, on specific boats, in specific engagements. USS Wahoo, under Commander Dudley Morton in 1943, conducted patrols in the Yellow Sea and the Sea of Japan that took the submarine into waters no American boat had worked before, far from any friendly port, days of transit away from any prospect of rescue if something went wrong below the engine room floor plates. Morton pressed his attacks aggressively and repeatedly, coming shallow when doctrine said to stay deep, engaging targets at ranges that left no margin for equipment failure. The engine room that supported those patrols ran without a recorded propulsion casualty across the patrols that Wahoo completed. The boat was eventually lost in the La Parao Strait in October of 1943 to causes the Japanese records suggest were depth charges and possibly aerial attack, not mechanical failure, not an engine casualty in an exposed position. The engine did its part. USS Tang, under Commander Richard O'Kane, conducted 5 patrols in 1944 that are among the most tactically productive in the American submarine record. Tang sank 33 ships across those patrols, a tonnage figure that placed her crew among the most effective in the submarine force. O'Kane pressed his attacks at ranges and from angles that required absolute confidence in his ability to maneuver at high speed. That confidence had a mechanical foundation. The engine room's performance across Tang's patrols is recorded in the maintenance logs as routine, adjustments made, inspections completed, hours accumulated without incident. The boat was eventually lost to a circular run by her own torpedo on her fifth patrol. The engine was not the variable that failed. The tactical reality of submarine warfare in the Pacific created demands on propulsion that the pre-war specifications had anticipated, but that only the combat record could fully confirm. A submarine making a surface attack at night, the standard approach doctrine that Morton and O'Kane and the other successful commanders refined through 1942 and 43, ran its engines at high power through the approach, required immediate response to throttle changes as the attack developed, and might need to execute a high-speed retirement on the surface if the target's escorts turned toward the firing position. The transition from high-power approach to emergency flank speed to battery charging transit home put the engine through load cycles that the bench testing had modeled, but that actual combat applied in sequences and durations no test cell could precisely replicate. The Fairbanks-Morse engine handled those cycles. The patrol records say so in the silence of their maintenance sections. The absence of propulsion casualties across hundreds of patrols is itself the testimony. The depth charge problem was a different kind of stress. When a submarine went deep under attack, the engines shut down and the boat ran on battery power. When the attack subsided and the boat crept away, sometimes hours later, sometimes the following night, the engines had to restart. They had been sitting cold in a hull that had been subjected to shock loading from depth charges detonating at varying distances. Shock that cracked hull fittings, unseated gaskets, shook loose connections throughout the boat. An engine that would not restart after a depth charge attack was an engine that left the crew with battery power only, and battery power in a Pacific Fleet submarine was a finite resource measured in hours. The Fairbanks-Morse engine restarted after depth charge attacks. It restarted because Wilson had designed it to tolerate shock loading, because the opposed-piston architecture's absence of a cylinder head eliminated one of the most common points of failure under vibration, and because the bearing specifications he had pushed through against procurement resistance were holding up to conditions far more severe than a test cell endurance run. The crews who restarted the engine after a depth charge attack and drove their boat toward open water did not think about bearing specifications. They thought about distance and course and the depth gauge, and whether the sound gear was still picking up the escort. The bearing specification was doing its work without their knowledge, which is exactly what a good engineering decision does. The Balao-class boats that followed the Gatos into service in 1943 and 1944 ran a refined version of the same engine. The core opposed-piston architecture was unchanged. Production quality had improved as the Oshkosh workforce accumulated experience. The Navy's maintenance manuals, written in collaboration with Fairbanks-Morse engineers, and revised to reflect what combat patrols had taught about the engine's actual wear patterns, gave the fleet's machinists better guidance than their predecessors had worked from. The feedback loop from patrol casualty reports to factory engineering responses to revised maintenance procedures was functioning the way the best wartime manufacturing arrangements functioned. The engine was getting better as the war progressed, its weaknesses refined away patrol by patrol. The patrol record that the Gato and Balao-classes compiled between 1942 and 1945 was the strategic engine of the Pacific Campaign in ways that the surface war and the air war sometimes obscure. American submarines sank approximately 5 million tons of Japanese merchant shipping over the course of the war. They sank cruisers, destroyers, and troop transports. They thinned the escort forces Japan needed to protect its supply lines, and could not replace quickly enough to stabilize the situation. The arithmetic of Japanese industrial production ran directly through the submarine campaign. The oil and bauxite and iron, or that Japanese industry required to sustain its war effort, had to move by sea from the occupied resource territories, and the American submarines were cutting that supply line systematically, patrol by patrol, from the fall of 1942 through the final months of the war. The shipping losses Japan absorbed in 1944 alone were sufficient to threaten the industrial base that kept its aircraft factories and naval yards running. By 1945, available Japanese merchant tonnage had been reduced to a fraction of what the war economy required. None of that was possible without an engine that worked. The torpedo failures that plagued the early patrols, the Mark 14's unreliable magnetic exploder, the contact fuses that failed to detonate on oblique hits, cost the submarine force targets in time that it could not recover. The crews adapted, learning to adjust firing angles, to distrust the features the Navy had spent years and money developing, to work with what the weapon actually was rather than what the specification claimed it was. They adapted because they were professionals. What they could not adapt around was a propulsion plant that failed at sea. A submarine without reliable main engines was a submarine that could not complete its transit, could not escape pursuers, could not bring its torpedoes to the firing position where the tactical skill of the crew converted range and angle into sinkings. The Fairbanks-Morse engine was the precondition for everything the submarine force accomplished. Its reliability was the silent variable in every patrol report, present in the entries that recorded no propulsion casualties and therefore required no explanation. The physical evidence of this record exists in archive collections in Wisconsin and in the Navy's own historical files. The engineering drawings that Wilson and his team produced, the test reports, the production record from the Oshkosh plant, all of it documents the output rates, the quality control procedures, the material specifications, and the Bureau of Ships inspection results that tracked each engine from the factory floor to the fitting out berths where submarines receive their machinery. What you are looking at, if you pull the Fairbanks-Morse technical submission to the Bureau of Ships from the spring of 1940, is a document that maps precisely onto the machinery that sat in the engine rooms of Wahoo, Trigger, Tang, Harder, and the other boats whose patrol records define what the American submarine war in the Pacific meant in practice. The drawings are clean and precise. The tolerances called out in dimensions that required machine tool capability the Oshkosh plant deliberately built toward. The engine that powered the Pacific submarine campaign was drawn on paper in Wisconsin and machined to those dimensions by men and women who never saw the sea. A preserved Fairbanks-Morse Opposed-Piston engine from a Balao-class submarine stands at the Submarine Force Museum in Groton, Connecticut. It sits as preserved machinery sits, clean and static, the oil long since drained, the crankshaft that once turned at between 250 and 300 revolutions per minute motionless under the museum lights. Stand next to it, and the engineering logic of the design is readable in the physical form. The two crankshafts connected by their vertical gear train, the cylinder porting arrangement that eliminated the conventional head, the proportions that gave it the power-to-weight ratio the submarines required. The men who ran this type of engine in combat knew it by sound and feel. The museum version is silent. The record of what it did when it was running is in the patrol reports and the tactical histories that post-war analysis assembled from both sides of the war. Wilson retired from Fairbanks-Morse in 1952. His engineering files were retained in the company archive. A technical history published by the Submarine Force Museum in the 1980s draws on those files and names Wilson in the acknowledgments. He does not appear in the index. The men whose boats his engine powered are in the index, as they should be. Wilson's contribution is the kind that registers, if it registers at all, in the footnotes of technical histories read by engineers who already know to look for it. The Fox River still runs through Oshkosh. The building where the production line operated was demolished decades ago, and the site has been redeveloped. There is no marker there recording what was manufactured on that ground between 1940 and 1945, no plaque naming the engineering team or the production workers who held the tolerances the design required. The submarines those engines powered have their memorials. The boats that were lost are listed at the Submarine Force Memorial in Pearl Harbor, the names of the men who went down with them cut into stone. The engine that carried those boats to the fight and, in most cases, carried them home again, is represented by the preserved unit in Groton and by the engineering files that a small number of researchers have worked through in the decades since the war. The account of Wilson and his engineering team, of the machinists who produced units to specification under wartime pressure, of the crews who trusted what had been built for them without knowing the name of the man who built it. This is the account the record supports. Where it is incomplete, the incompleteness is the record's own. The names of the individual machinists who ran the production line are not in the surviving files. The internal debates about the bearing material change are reconstructed from engineering revision documents rather than from personal testimony. Wilson left no memoir. What he left was the work, and the work sailed on 341 war patrols and came back from 277 of them. The 64 boats that did not return took their engine rooms to the bottom of the Pacific, where many still lie. The boats that came home brought their engines back to the tenders and the base repair facilities, where the machinist's mates logged the hours and the Bureau of Ships compiled the maintenance records that confirmed, patrol after patrol and year after year, that the engine designed in Oshkosh in the late 1930s was exactly the engine the United States needed for the war it had to fight. The men who designed it never fired a torpedo. They never dug beneath a destroyer's sonar sweep or sat in a flooded compartment listening to the hull creak at 400 feet. Their war was fought at drawing boards and test rigs and production floor meetings in Wisconsin. The connection between that work and the work done at depth in the Pacific is the kind of connection that military history rarely traces all the way back to its source. This account has tried to trace it. The source is in Oshkosh, on the bank of the Fox River, in the winter of 1938, where an engineering team sat down with a problem that looked unsolvable and found, through the particular discipline of people who refused to accept an apology as an answer, that it was not. Thank you for staying with this until the end. If what you heard here stayed with you, the other films on your screen carry the story forward. Subscribe if you haven't, and I'll see you in the next one.